Hi. Hello. I guess I need to talk right into the mic. So I'm going to talk about the IETF Trill protocol. How many people here, I don't know, have never heard of it? Everybody's heard about it at least. I guess if you haven't heard about it, you wouldn't come. So anyway, I have a fair number of slides, so I want to kind of move through them here. Hopefully there'll be some time at the end of each part for questions. I'll be here between the two parts for questions also. So if you want to know who I am, I'm with Huawei, principal engineer there. I've worked for Cisco before that and Motorola Labs before that. So I'm the co-chair of the Trill working group, which is the primary reason I'm giving this. I also have other positions. I'm chair of the point-to-point protocol extensions working group and stuff. And you should note that this is just sort of my opinion. It's not claimed to be an official opinion by the Trill working group or by Huawei as such. So here are the things I'm going to be covering in the two parts. I realize the second part is shorter, so even though I have roughly the same number of topics, I have fewer slides. So what is Trill? So it stands for Transparent Interconnection of Lots of Links. Here's a pointer to the charter, so I guess you'll be able to get these slides. You can just click through or whatever to get there. It's co-chaired by myself and by Eric Nordmark of Cisco. The devices that implement it are called R bridges or routing bridges or Trill routers. And an area that makes use of Trill is called a Trill campus or an R bridge campus. It's kind of like a bridged LAN, except instead of bridges, it uses R bridges. So it's a compatible protocol. The end stations or layer 3 routers, IP routers that are connected to a Trill campus, just think they're connected to Ethernet. They don't really know any different. If you take an existing network and you take your 802.1q bridges and you replace those with R bridges, then as you can do that incrementally, the network will still operate correctly. And as you do that, the network stability improves and the bisectional bandwidth and use of your links and so forth will improve. And one of the great features is that spanning tree is never built through an R bridge. If you have a bridged LAN section of your network, you can obviously be running spanning tree within that bridged section, but the spanning trees, you can even, if you want to have it, the port of your R bridge kind of included, but an R bridge, a spanning tree is never built between the ports of an R bridge. In other words, the tree never extends through R bridges. So R bridges basically cut up your spanning tree and make it smaller, which is a good thing. Makes it settle faster, be more stable. The idea behind Trill is very simple. I think all great ideas are simple. You take a native frame from an end station or a layer 3 router, which is really considered an end station in this context. You encapsulate it, you add a hop count and so forth, and you route that encapsulated frame using ISIS, and then you decapsulate the frame before delivery. So this slide shows you the basic idea behind Trill, and it's really quite simple. So it provides a bunch of features. The sort of highest level, most important ones, you get least cost paths. So your frames follow, unicast frames follow least cost paths through the network. You get equal cost multipathing for your unicast traffic. And the way Trill is designed, you can also multipath, multi-destination traffic. So I'm just going to go over some of these features. Some of you probably find this a little basic, but go along. So here we have a network with 3 bridges and a bunch of end stations. So if you run a spanning tree on this, spanning tree will cause there not to be a loop. And it does that by disabling a port. So in this case, it's disabled the bottom left port there from B3. So if you have traffic in this network, if it's between the end stations connected to B2 and B3, those are intended to be bridges, it takes an extra hop through B1 because of a spanning tree. So if you replace those bridges with Trill switches or routing bridges, then there isn't no port disablement, and assuming all 3 links are functioning, your traffic will follow the least cost path and will only be 1 hop between any pair of these. So in multipathing, here we have traffic from the left coming into B3 and intended for B2, and spanning tree will similarly disable enough ports to make sure you don't have any loops here. And even if you could somehow convince spanning tree to enable more stuff, B2 would likely to get very confused if you were multipathing traffic on different paths between B3 and B2, because B2 would be seeing the possibly traffic arriving on different ports from the same source address, and that would tend to make it kind of upset. But with Trill and R bridges, you replace these bridges with R bridges, you can have all of the links in use, and actually this one in the center here is RB5. There's no particular reason for that to be an R bridge. Since Trill and bridging is compatible, that could still be a 802.1q bridge if you wanted. And in this case, you get much improved bandwidth. You do have to be sure you send a particular flow along a particular path, or you'll get reordering. But that's known technology. And the reason that this R bridge over here isn't confused is that these things are really Trill routers. It's like any router. They have a link header on the outside which changes on a hop-by-hop basis. So the frames arriving here, the outer header has the source address for the previous R bridge or Trill switch. But the true source is encapsulated inside the frame. So just to kind of summarize some features of bridges and layer 3 routers, and mention that Trill routers have sort of the combination of these features. So bridges are great because of their transparency. You can take any kind of traffic, and with a very tiny corner case of some bridge control messages, they all get through transparently. You can plug and play, the zero configuration, depending on what features you want to use. If you want to use VLANs, you have to configure them, but you can get your traffic through to in a pretty well plug and play fashion. They do support VLANs, and it's been extended to have more than 4,000 tenants if you have things like 802.1 AH with the 24-bit service identifier. They have a frame priority system for prioritizing your traffic. And there's a number of data center bridging features that have been added to enable lossless Ethernet, at least no loss in due to queue overflow, and virtualization, virtual bridging at the edge. So routers are great for multipathing. That's the thing they do quite well. They can find optimal paths, least cost paths. Rapid failover. Rapid spanning tree fails over pretty rapidly, but under certain circumstances, root bridge failures can take a number of seconds before the network will recover. Routers typically have the safety of a TTL, and it's important that the TTL is implemented in the data plane. As switches get more and more complex, with increasing numbers of protocols and more complex protocols, there's an increasing probability of a mode of failure where the control plane fails, but the data plane continues to operate. And the problem with that is that then all of the wonderful demonstrations and proofs that your routing protocol is loop-free or will operate properly and so on and so forth, almost all of those proofs have this assumption that the control plane is still functional. The routing protocol is actually operating. But if the control plane crashes but the data plane continues to route or forward your traffic, that assumption isn't true and all these proofs fall apart. But if you have a TTL that's implemented in the data plane, then at least you know that if you have transient or maybe some longer problems while you're rebooting things or getting things back together, that the traffic will decay eventually and as the TTL counts out. And typically routers have more in the way of options and extensions and things like that. So Trill routers support, can support all of these features, both of features of routers and the features of bridges. So a few more things. Mentioned before, Trill is designed to break up spanning tree. It's a thesis of Trill that spanning tree is bad. The less of it you have, the better off you are. The unicast forwarding tables at Trill routers scale with the number of R bridges in your campus. So does not scale with the number of end stations. And the transit R bridges in the middle that are forwarding traffic never need to learn the end station MAC addresses. Of course, it's compatible with IP routers. A Trill campus is as transparent to an IP router as a bridged LAN is. So IP routers don't need to know anything about Trill. It just looks like a Ethernet network to them. Trill does have MTU feature, so it can actually test and determine the MTU of links, and it can be sure that it operates safely. It doesn't have any. It won't try to send any control PDUs that would be blocked by MTU problem. And in fact, if you do have a jumbo frame network, or maybe one with can accommodate 2,500 byte frames for FCOE or something, then you can in fact also use jumbo routing control frames, like your link state, your PDUs and things like that can be larger. And Trill has a poem. So not very many routing protocols have poems. Matter of fact, the only other case I know of is the spanning tree algorithm, which has a program called Algorime, which you can probably find easily on the network if you want. So this is the poem for Trill. It was written by Radio Perlman's son. It says, "I hope that we shall one day see a graph more lovely than a tree, a graph to boost efficiency while still configuration free, a network where our bridges can route packets to their target LAN. The paths they find to our relation are least cost paths to destination. With packet hop counts we now see the network need not be loop free. Our bridges work transparently without a common spanning tree." So you might guess from this that Radio Perlman in fact designed Trill. So I have some history here that I wanted to just go through quickly. Is how Trill came about and what its current status is. So I wasn't sure how far to go back. So I started in 1964 when packet switching was invented. That seemed like a good place to start. Not clear it's worth going much further back than that. And then Ethernet was invented. And then link state routing was invented. So routing came well before bridging. Link state routing is really quite old. Invented in '79. In 1985, Radio Perlman invented the spanning tree protocol, initially just kind of to hook together Ethernet segments. In 1987, she designed DECnet Phase 5, which really became ISOized into ISIS. So she designed that protocol. And an interesting event happened in 2002. Beth Israel Deaconess Hospital, it's a hospital in Boston, Massachusetts. They had acquired a number of other clinics and so forth, and they just kept hooking the networks together. And they ran it all as one big layer 2 network. And suddenly one day, the whole thing melted down due to spanning tree failures. I believe the maximum diameter for classic spanning tree had been exceeded. So there was actually an article in the Boston public newspapers that mentioned spanning tree algorithm and failure. And it's not very common that you see spanning tree algorithm mentioned in the normal, ordinary newspapers. But so as a result of this, Radio decided that there needed to be a better way. She never really liked spanning tree that much because she thought it was inherently somewhat unsafe. So she came up with Trill, and she presented it to Infocom initially. And in 2005, she went to IEEE and presented it there, and they really weren't very interested. They thought they had all the solutions. So she went to the IETF, and the IETF said, sure. So a chartered working group was formed, Trill, in the IETF. And in a few years, it usually takes longer than you would think reasonable to get any standards work done. People thought that Trill was complete. But the first time it was actually attempted to really deploy a software version of Trill, it ran into problems due to some pretty old legacy equipment which strictly enforced the classic Ethernet MTU maximum. So it decided that really it needed to be more MTU aware and have this MTU feature that I mentioned earlier. And those fixes were incorporated. 2009, the problem statement and Trill applicability statement were issued as an RFC, and the working group passed up to the IESG, the Internet Engineering Steering Group, which is the group that has the standard setting authority in the IETF, the Trill standard. So that's 2009. So then it took a while, and in 2010, in March 15th of that year, Trill was approved and became an IETF standard. Also in 2010, the various ether types and multicast addresses and so forth required were assigned a network layer protocol ID. And there was a successful Trill control plane interop at the University of New Hampshire. So, but the RFCs actually were not published in 2010, the basic RFCs, because of various factors, including interdependencies between the RFCs and some, I might say, other political problems. The RFCs were actually published in 2011, and the most important one is RFC 6325. That's the Trill base protocol. And that also includes the specifications for Trill operation over Ethernet. Although Trill assumes that the end stations and layer 3 routers that it's providing service for are connected to it by Ethernet, or something you can easily map to Ethernet, the connections within the Trill cloud, the connections between our bridges or between Trill routers can actually be any technology, because Trill routers are routers, so they can do whatever they need to on a hop-by-hop basis. So Ethernet, of course, is the most common. At the same time, because you can probably tell because they have sequential numbers, the Trill use of ISIS was published, which gives the ISIS code points for use in Trill. A document giving more details on adjacency formation, very detailed state machines and so forth was also published. And then later in that year, Trill over a point-to-point protocol was published as an example of another protocol you can use between Trill routers, between R bridges. And yet another document with sort of more very explicit detail in state machines on the appointed forwarder mechanism was published that year. So this is 2012, so what's happening this year? Well, there's a bunch of drafts that have been approved, and so they're now IETF standards, but they haven't actually issued as RFCs, also for some dependency problems. So BFD over Trill has been approved, and so these are URLs to the drafts, but all the ones here are actually also in the RFC editor's queue to be published as RFCs. They've gotten final approval. There's an R-bridge channel mechanism, which is a way for sort of sending arbitrary protocols between R-bridges themselves, not involving end stations and so forth. And so the BFD uses the channel support, R-bridge channel support, some header extensions, and then a sort of an omnibus thing. So notice at this point, 2012, it's now 3 years since the initial approval of Trill in 2009. And so there have been some cases were found where some clarifications and corrections were needed or some updates to some parts. So that's kind of the history of how things have been going. I'll give more on the standardization status later. So I want to go over a couple examples of things you can do with Trill. So the first one is sort of an industrial control kind of thing. It says power plant, but it could be a chemical processing plant or who knows what. And the little black dots at the top and the bottom would be like temperature sensors or pressure sensors or automated valve controls or whatever. So for large industrial facilities like power plants and so forth, people do tend to use Ethernet. But the control protocols that they use in some cases are protocols that nobody makes routers for, so you really kind of have to use a bridge network. So in this case, it's a fairly normal structure here in that there's sort of access bridges and aggregation bridges and then some core bridges. And of course, you have to have two of everything. And this all forms one large spanning tree domain, rapid spanning tree. And because of spanning tree, vast amounts of this is disabled, and you're really only using half of the equipment in many cases. So what could we do to this and make things better by using Trill? One problem with this is that if one of the core bridges, which is probably configured to be root, fails, it can take 5 or 6 seconds for things to get back together. And some of these control protocols, if they detect lack of communication for more than 1 second, assume that there's been a significant failure. So like if you have a nuclear power plant and your nuclear power plant scrams and shuts down because a piece of networking equipment failed, it's not only like not really good, you know, you also, at least if it's the United States, you have to file lots of paperwork with the government and, you know, for any failure like that. And, you know, people will be willing to go to quite a bit of effort to avoid this. So let's say that first thing we want to do, we just try replacing these core bridges with Trill switches, Trill routers. So if we do that, it looks kind of like this. We have core R bridges in the center. We still have the access bridges and the aggregation bridges. But as I said, spanning tree is terminated by Trill. So as a result, instead of one spanning tree domain, we actually have 3. Of course, this is a somewhat simplified diagram. Maybe it's 10 or something like that in a real plant. So then this would result of just replacing the core bridges with R bridges running Trill. So what happens if we try to just go one level further and replace the aggregation bridges with Trill switches? Well, if we do that, we actually don't need the core switches very much anymore. Trill works great in a mesh-like environment. So if we do that, we really have effectively reduced the spanning tree domains to the single access bridges. And a spanning tree domain of a spanning tree domain consisting of only one bridge is really very stable and settles very quickly, so that's not a problem. The second example I want to show is a little bit more data center oriented. Maybe. So here we have a case where we have a data center, and this is a fairly common kind of thing. We have head of rack bridges and some distribution bridges and routers going to the outside world. So there's, using spanning tree, there's really going to only be one path between these head of rack bridges, or at least only one path per VLAN. And as a result, and we really kind of want to only have two of these here because having more doesn't really help that much with spanning tree. And the result is that these distribution bridges have to be really very solid, probably pretty expensive, and each one wants to be able to handle the entire traffic. So if there's a failure of the other one, or if you're doing maintenance on the other one or something like that. So you have sort of one backup kind of thing here. If we replace these devices with Trill routers, then we can have something that looks more like this. So we have head of rack Trill routers down here and distribution R bridges. So you'd have multiple paths where different flows, even within the same VLAN, can be spread over different paths. You can have lots of these. It all works fine. There's no particular disadvantage to that. And in fact, there's the advantage that if you had, say, 5 of them, then as long as each one could handle a quarter of the traffic, one of them could fail, or you could be doing maintenance on one of them, and you can still have your traffic handled fine by all the others. It's more like N1 backup. And if you actually have more failures, it degrades more gracefully. So those are 2 examples of Trill. So the next section is probably the kind of the longer ones and a little more detailed technically, which is sort of really how Trill works at a somewhat lower level. I'm talking about the features and giving some examples, and this is how it actually sort of happens. So I mentioned before one of the primary ideas behind Trill is encapsulation and with a Trill header. So the data frames that are going between Trill routers are encapsulated, and they have, after encapsulate, they have this Trill header added, and then they have an outer link header added to them. So the local link header is really just to get from one Trill router to the next one. It's like the one-hop forwarding. So it has like this, if it's an Ethernet link, it has the source and destination address for 2 adjacent R bridges. And those addresses get sort of swapped at each hop if it's all Ethernet in typical router-like fashion. And if it's unicast, then it's if it's over a multi-access link, like it could be bridged LAN or something, be one of these links, then it's a unicast addressed to the next switch on the path towards your destination. But Trill has facilities for handling multicast and broadcast and flooding unknown unicast addresses and things like that. And in those cases, then over Ethernet, the Trill data frames are sent to the all R bridges multicast address. So that's the outer header. The link header comes right after that, specifies the R bridge that received the original native frame, the ingress R bridge, is the one that did the encapsulation. And if it's a unicast frame, it also has the egress, that is to say the R bridge that's going to finally deliver the data to the ultimate destination. Or if it's a multicast or broadcast frame or whatever, then it has, instead of the specific identity of the destination R bridge, it has the identity of a distribution tree. So Trill does use trees. They're not calculated the same way, but they're only used for multi-destination frames. So there's a bunch of reasons for this. One is the Trill header in this encapsulation provides a place for a hop count. I mean, Ethernet was never intended to be connected together in bridges and routers and things like that. And so there's no space. Well, no space was ever provided in the Ethernet header, the initial Ethernet header for hop count. It hides the original source address. The original source address is inside the encapsulation, as I'll show in more detail in a minute. So that avoids, if you have any bridges along the way, they will not get confused by possibly receiving frames from different directions with the same source address. When they receive a frame, it just has the previous, immediately previous hop R bridges as the source address. And this whole encapsulation scheme means that for these frames, you can forward them based on for unicast, you can forward it based entirely on the Trill header. So all you need to know is this egress R bridge identity. you don't need to know the destination MAC address or ever look at that in the process of forwarding unicast. For multi-destination, you also really only need to know the tree. It is common, all current implementations I know about do look a little bit further in and do check the true VLAN of the data, because they don't want to flood it over an entire distribution tree if that goes to some parts of the network where that VLAN is not present. So they do prune the tree. So as a result, the forwarding tables at the transit arbiters really only need to scale with the number of Trill routers, not with the number of end stations. And also, because you've done this encapsulation, there's this separate outer link header. Well, you can put a VLAN tag out there if you want. It's not the real VLAN of the data. It's just the VLAN part of the hop-by-hop link header, and that may be necessary. For example, you might have two areas that were connected by carrier Ethernet facilities, and the carrier has said, you can send whatever you want to over this, but it has to be in VLAN 42. Well, you could do that fine with Trill. You just put a VLAN 42 tag on the outside, and the true VLAN of the data is inside the encapsulation. So what does this Trill header looks like? This is a Trill header. It's pretty small. It's got these nickname fields down here, which are 16 bits, and you can configure them statically if you want, but they're normally auto-configured. It's designed, that's the easiest thing to do. And this is the arbridge that receives the frame, and this is where it's going to go if it's unicast. There's a version field, which is currently always 0, and some reserved bits. The M field is actually very important, the M bit. That bit is 0 for unicast frames you're sending to a known egress, and that's 1 for multi-destination frames, which are multicast frames, broadcast frames, and unknown unicast. There's also the hop limit, and there's an extension length figure. You can do extensions to the header. So I have this grayed out ether type up here. People kind of think of the Trill ether type as being part of the Trill header, but strictly speaking, that's not true. You only need the Trill ether type there for a Trill data frame going over an Ethernet link. If you're going over some other kind of link, you may have know in some other way that it's Trill data. And I'll show examples of that. So here's actually more detailed diagrams of what Trill over Ethernet actually looks like. And there's two kinds of Trill frames. There's the Trill data frames, and then there's the ISIS control frames. So for Trill data, this is the Trill header here, and the Trill ether type is 22F2, and if it's over Ethernet, you need that there. And then this is the link header. So this is really what you need to get it from one arbridge to the next. And if you have a completely Ethernet network, which is of course very common, then you'd always have the ether type there. So people sometimes think of the ether type as being part of the Trill header, but that's not strictly speaking true. Then this is the payload. So this is the original destination MAC address, the original source address, and the VLAN, or actually Trill is being extended so you can have a tenant identifier with more than 4,000 tenants, and the actual user data, and of course the frame checksum. So this VLAN tag out here doesn't have to be there. It's only really needed if there's a VLAN sensitive link where you need to put some outer VLAN tag to get the data through. And the ISIS frames are a little simpler. You have the ISIS PDU. It looks the same as it does normally, layer 3 kind of thing. And one interesting thing is in Trill, the ISIS PDUs are ether type encoded. And there's a layer 2 ISIS ether type, 22F4, assigned at the same time. And so in normal layer 3 ISIS, it uses LLC encoding rather than ether type encoding. And the use of LLC encoding means you're strictly limited to the classic Ethernet size maximum. But as I say, Trill has this MTU feature where it can make sure that it knows how big the links are, and it can set the MTU that's used for the size of these ISIS control frames to be larger than the classic Ethernet maximum, as long as it's less than the link, the active link in your network, which has the smallest MTU. So you can actually have, with ether type encoding, you can have ISIS PDUs that are jumbo frames. There's a few special types of ISIS frames that doesn't apply to for loop safety reasons, but for link state packets, which is the primary concern usually, then you can have jumbo frames. So there's Ethernet. So looking at it's an example of another technology, since the links between arbridges, the links inside the Trill cloud can be other technologies. This is what it looks like for point-to-point protocol. And I think the main point in here is that in point-to-point protocol, of course, there's no outer MAC addresses. It's point-to-point, and it's only one other place you can go. There's no ether types because you've negotiated Trill on your PPP link, and all you need is the right PPP code point. So there's been PPP code points allocated for Trill data and for Trill ISIs. And that usually there's a FCS for PPP, which is somewhat different. So that's an example of a different technology. There's a draft on Trill over IP. So you could have like a couple small data centers, and both of them just have general access to internet IP or something like that. You might want to form a tunnel through that, and where you can treat the internet as just a link between your 2 or 3 or whatever smaller data centers, and kind of bind them all into one large data center. So there's a draft on how to do that. It hasn't progressed as far as some of these other drafts. But what I want to do next is go through the actual step-by-step processing for an Ethernet frame coming from an end station, being ingressed by an R bridge, going through a transit hop, and being egressed by an R bridge and being delivered to some other end station at the other end. So here's this the input port. So Trill switch ports are like 802.1q ports in the sense that when a frame comes in, it always gets assigned VLAN ID and priority. I mean, if it's VLAN tagged, that's pretty obvious, but if not, it defaults depending on the port, or you can do it in other ways too. So usually that data is really sort of separate metadata, but it's kind of logically as if the VLAN and priority were added through a VLAN tag in the frame. So this was what, perhaps the top, if it was untagged, was what the end station sent as a native frame, and this is kind of after it goes through the port logically. So now we're ingressing the unicast frame in the Trill logic. So what do we do with this whole frame? Well, we take everything but the FCS and we encapsulate that. So that sort of stuff becomes frozen, including the actual VLAN identity of the data. And then we look up the destination MAC and VLAN. And I'm assuming this is a unicast address where we know where it is in the network. So we go look it up and we find out what is the egress R bridge, that is, say, the last R bridge on the way to delivering to this addressed end station at this destination MAC and this VLAN. What is the, and I'm assuming all Ethernet links, what's the output port, and what is the destination address of the next hop, the next R bridge along the path. So using the egress R bridge nickname, we can construct the Trill header, and we presumably are configured to put in a TTL here. And the R bridge that's actually doing this processing, the ingress R bridge, puts its own nickname in here, and that's used for data plane learning of MAC connectivity and things like that. So that's the Trill header. And then, because we're assuming it's Ethernet, we have to put the Ethernet stuff on here. So we have to add an Ethernet header, and we looked up the destination address for the next R bridge, and we know what port it's going out of, so we know what the MAC address of our port is we're about to send it on, and then we add a FCS. So this is all logical. Usually FCS is calculated at a low level as it goes out the port. So now we have a Trill data frame encapsulated in everything, and what happens at a transit hop. So this is exactly like it was on the previous page. It comes in like this. What do we do? Well, we're going to forward all this data. We first would decrement the TTL, and if it goes to 0, we discard it. You know, it's pretty obvious. We need to do a lookup, but the lookup here for a transit case is just based on the egress nickname. So this is just a 16-bit field. So this is a very simple, easy lookup here, and we just need to look up what the next hop is. So the next output port and destination address. And of course, if we're doing ECMP, there might be a list of output ports and MAC addresses, and we might need to do something to determine what flow we consider this in and choose between these equal cost paths. But I'm just assuming simple forwarding here for this example. So using this stuff we've looked up, we can construct the output. And this is what we send on the next hop with the decremented TTL. And of course, things may have changed here. Things will have changed. So we have to calculate a new FCS. So it goes hop by hop like that. When it finally gets to the egress, what the egress processing does is decapsulates it, and it detects that it's the egress because it knows what its own nickname is, and it sees that its nickname in the header here. So it basically pulls out the payload like this, and really discards the last hop by hop link header, and it still has to do one more lookup to determine which of its ports to send this out based on the destination MAC and VLAN. And you know, there's various contingencies. It could conceivably have been forwarded in this way, believing it was a known unicast, until it finally gets to the egress arbridge. It could be that for some reason, due to MAC table overflow or whatever, that egress arbridge could have forgotten the destination MAC. So if this lookup fails, then it basically floods it out all the ports in that VLAN, but just from that one arbridge, just locally. So one last step. So we're sending it out the output port now in native form. We no longer have any of the Trill encapsulation or stuff. Of course, the output port, if the end station we're sending it to is VLAN ignorant, may be configured to remove the VLAN tag. So we may end up sending something more like this to the end station. So that's the whole sequence of processing. So it's talking about how you can do that, how Trill sort of gets its act together and can manage to do all these things. It's based on ISIS. And the very first thing that happens when you turn on Trill router is that it emits hellos, ISIS hellos, with some very minor modifications for Trill. And that's by sending and receiving these hellos, indicating who they can hear and so forth on each link. Each arbridge develops an idea of all the adjacencies, and it has an idea of the cost to those adjacencies based on the line speed by default, but can be configured. So then this information is reliably flooded. So every arbridge in the campus knows what the connectivity, adjacency of all the other arbridges are. And based on that information, then each arbridge can calculate the topology for the whole network, and it can figure out what the least cost path is to any destination arbridge. And for forwarding stuff, it really only has to know about destination arbridges. So, and if it wants to do ECMP, then it can remember multiple paths that are the same least cost to some destination. And as I say, Trill handles multi-destination frames. The information in this link state database is enough so that using the rules defined in the Trill protocol, each arbridge calculates the same distribution trees. And there's a minimum of one, but a lot of implementations you'd go with a couple distribution trees. You can have more, and that way, when it gets a frame to forward and a distribution tree, it knows how to pick which output ports, and it will make the same assumptions, and basically have a loop-free distribution tree. This flooded information is used to support various other features in Trill as well. So one question is, why was ISIS chosen when like OSPF seemed like another possible choice? And there basically were two reasons. One was that it was possible to do ISIS with zero configuration. You don't need to assign IP addresses to your machines. And ISIS has a very flexible data encoding, so it's easy to add fields. I think OSPF has been improved in that regard, but at least at the time, OSPF was more limited. So I mentioned these nicknames. They're 2-byte names for arbridges. The arbridges have ISIS system IDs, but they're much bigger. And Trill uses these nicknames in the headers. There's a couple reasons for that. One is it saves space. And the other is it's useful on some occasions for an arbridge to actually hold more than one nickname. There are two reasons for that. One is so that it can be a root of multiple trees, which as I'll get to in a little bit. And the other is you may want to have frames that are destined to go to the same arbridge, but in different ways. So you could have ones that use the least cost forwarding and ones that use, for example, traffic engineered forwarding. And there's a draft on that, which is not yet approved. So all this is how you can do, how arbridges learn about each other and how to get to them. But you do have to learn the MAC addresses also. So by default, the edge arbridges, the ones that receive the native frames, learn the source address. And whenever an arbridge decapsulates a native frame and sends it out, it learns the encapsulated source address and the ingress arbridge that encapsulated that frame. So it assumes that MAC address is attached to that ingress arbridge. There are ways to send MAC addresses through the control plane in Trill called ASADI. Not widely used as of yet, and you can of course always statically configure this sort of information. So the transit arbridges don't need to learn any of these MAC addresses. They can forward just based on the Trill header, and the if it's multi-destination and it wants to be more efficient, it can also look at the inner VLAN. So Trill generally supports multi-access links, and you may want to have multiple arbridges on some edge link with end stations. So here's an example where we have 3 arbridges on this link. So the way that's handled is one of the arbridges is selected as the designated arbridge. It's really the same as the designated intermediate system in ISIS. So by default, it would be in charge of all the native traffic on and off this frame. So the Trill data, encapsulated data, can go over this frame unless you disable it, which you might want to, because you might not want Trill traffic going over this. But the native frames are ingressed or egressed by these arbridges, and the designated arbridge is by default in charge, but it can assign things. So for example, if RB1 is elected to be designated arbridge, it could decide to handle the lower numbered VLANs below 2000 and assign RB2 to handle 2000 and up. So one you might wonder is, well, this is a very interesting looking thing down here, but really these days all links are, Ethernet links pretty much are point to point. So how is it that it looks like this? And the answer would be that this would probably really be realized by having bridges down there. So that basically a bridged LAN looks to Trill just like a multi-access Ethernet link. So as I think I mentioned, the multi-destination traffic is sent on a tree. The route is put into the egress arbridge slot. And the ingress arbridge, the one that first encapsulates, is the one that selects the tree, and it stays on that tree as is distributed. So all the arbridges in the campus calculate the same trees. So you have to be more careful about multi-destination frames because there can be forks in the tree. So if you have a transit loop for unicast, the TTL will save you. But if you have a transit loop for multi-destination, it could be that it'll be, as it goes around the loop, it's spewing out more copies because of forks in the distribution tree. And to fix that, there's a reverse path forwarding check. So when a Trill router receives a frame, it checks to see that it's arriving on the port that it expects it should arrive, given the ingress and given the tree that's being used. Let's see. So the trees can be pruned, this says. So Trill, the arbridges advertise what VLANs they're interested in, what end stations they have, and what multicast groups they're interested in, and whether they're connected to a multicast router. So a Trill router can decide not to send a frame down some branch of the tree if it knows there's no arbridge down that branch that is listening for that VLAN or interested in that group. So here's an example of a Trill campus with 3 trees, red tree, a blue tree, and a green tree. So like RB2 receiving a frame could choose any one of these. And this drawing might look a little odd. It's partly because I've actually chosen to route 2 different trees at RB2. That would mean RB2 would have to have 2 different nicknames, and either one of those could be put in the egress slot to go on either the green or blue tree. And you might want to do that if RB2 was the source or destination for a huge amount of multi-destination traffic, because that would enable you to spread the traffic over more links. You notice that although some of these links are part of both trees, many of them are part of only one tree. So I believe I'm actually out of time for section 1. So I didn't quite get to the last topic here. So I guess I will go into that at the beginning of part 2 after the break.
Okay, thank you very much.